So let's start by actually using Gram-Schmidt to find orthogonal basis. So this is going to be problem 01 from 6.4. So given a basis for W, find an orthogonal basis using Gram-Schmidt. So our basis vectors are going to be 3, 0, -1, and 8, 5, -6. So take a little bit to try and find an orthogonal basis. Do you guys need a little bit more time, or are you all right?
Maybe a little more time.
All right, yeah. Are we ready about now? All right, so does anyone remember the Gram-Schmidt process in the abstract first?
Wait, so first you set the first vector equal to v1.
Yeah, so you want v1, and we can just take this vector and keep it. Yep. And then what?
And then you
And-
find, oh, go ahead, sorry.
Oh, it's okay. You can go.
Okay, so you find v2 using v1. So you first do x2, like the second vector, minus,
Oh, x is this vector here?
yeah.
Okay.
Oh yeah, I meant v2 is, yeah, equal to the second vector, 8, 5, negative 6. And then minus the dot product of x2 and v1 over the dot product of v1 and v1,
2 dot
which is
v1 over v1 dot v1. And is that all?
and then that whole thing times v1.
Times v1. Will everyone agree with this? So what's this v2 representing? I guess first, what's the second term representing here?
The whole term or like the fraction?
This whole term, yeah.
It's like the part of x2 that's like in the span of v1.
Yeah, and that's exactly the projection onto the subspace of W. Span of V1 of x2, right? So essentially what's happening here is we're trying to find a basis. Like, let's say we have these two linearly independent vectors, right? To get this v2, what we're trying to do is find this vector here that's orthogonal to x1. And to do that, we're taking this x2 vector, projecting it to x1. And this is that projection, say x2 hat, and subtracting that from x2 to get x1, right? So our top term is going to be 8, 5, minus 6, dot 3, 0, minus 1. And the bottom is 3, 0, minus 1, dot itself, all times v1. What did you guys get for this numerical value?
Nine zero negative 3. Or wait, you mean just the part on the left or the whole thing?
Either one.
9 0 negative 3 for all of it.
Okay, so this is equal to 9, 0, negative 3. And then we subtract 8, 5, negative 6, or subtract that from 8, 5, negative 6 rather. It's fine, v2. Minus 9, 0, negative 3. So do we all get -1, 5, -9? Oh wait, that should be -3, not -9. Cool. Now, what would I do if instead of just this orthogonal basis v1, v2, I want an orthonormal basis?
You would have to simplify, so the V1 and V2 are in terms of zeros and ones, correct?
Not quite. So what's the definition of an orthonormal basis? There's two parts to it.
I know the dot product of itself has to equal 1.
So that's one of the conditions. So v dot v is equal to 1. And what else?
They're an orthogonal set.
Yeah. So we already have an orthogonal set, but we're missing this condition here, right? And really, this is the same thing as saying that the magnitude of the vector is 1, right? Because the magnitude squared, 1 squared is also 1. So really, we're looking for unit vectors that are now orthogonal. So these vectors point in whatever direction R3, and all we have to do is make them unit vectors. So to get unit vectors, we can take the vector and divide it by its magnitude. Right? So our V1 was 3, 0, -1. So let's say W1 is 3, 0, -1 times 1/10. And then W2 is -1, 5, -3 times 1/35. Right? Or actually, I think we need the square root of those. There we go. Any questions about Gram-Schmidt? Let's try a problem from 6.5 now. So we're going to find a least squares solution of ax equals b by constructing a normal equation for x, or x hat rather, and then b solving for x hat. And we're going to do this with a equal to -1, 2, 1, comma 2, -3, 3. And then b is equal to 4, 1, 2. So take a couple minutes to work that one out.
There should be a -1 on the bottom left, I think.
Oh, you're right. Yeah, in the book, there's -1 there. Good catch. My bad. Do you guys need more time or are you all right? All right, cool. So what's the normal equations this look like?
That'd be A transform times A times X equals ATB.
Yep. So we're going to need to compute this matrix here and this vector here, right? So what did you guys get for A transpose A?
Six, -11, -11, 22.
Did everyone else get that? Cool. And then A transpose B. What vector do we get here?
-4, 11.
Everyone else got that? Cool. So then we're just trying to solve this augmented system, right? 6, -11, -4, 11, 22, -11. And what does that come out to?
One zero zero 132.
0.
Going
Oh,
going down. 100132.
3, 2. So we found our vector x hat as 3, 2, right? And how do we actually find the vector in our column space and find distance?
Column space is A x hat, and
Yeah.
then distance is B minus that.
So if we actually want the vector in our image that's the closest to B, we plug x in and do that multiplication. And that gives us our vector in col A closest to B. And the actual distance will just be B minus that vector. Or you want the magnitude of this vector. Questions about that one?
Yeah, there's like some theorem in the book. It's like close to the end. It says like instead of like row reducing, you can just take the inverse of like the left and then multiply it by the right.
Theorem 14?
Yeah, 14.
Yeah, so really this set of normal equations we have here, it's a question in terms of A transpose, right? This AX is some vector, and this B is some vector. So we're trying to actually like find out something about A transpose. But the thing is, we don't actually know a lot about like A or A transpose individually. Sure, we have this nice kind of expression ATA, which is going to be a symmetric matrix. But in general, if we wanted to write this as one equation, where if we wrote x hat is ATA inverse ATB, right? Here we're multiplying by A transpose A inverse on the left. To be able to actually do that, we need to say that this matrix has an inverse, right? So we can do that if the columns of A are linearly independent. because then A transpose A will have an inverse.
So like, should we like check if it's like linearly independent when we do it, or do we just like assume it is, or like just do the normal way where we
So
don't do
if
that?
you know the columns are linearly independent, then this is going to be faster. But in general, this way will always work, even if your column vectors aren't linearly independent, because this isn't assuming anything about A, right? Like you could get this system, augmented system that actually is inconsistent, and you like, sorry, not inconsistent. If you try to do this inverse, you might not be able to like actually finish the problem. Whereas if you do it this way, no matter which columns you actually end up having, this system won't be inconsistent.
Okay.
Because this requires you to actually find this inverse, which may not exist. Other questions? Let's try, let me make sure this one wasn't assigned. Yeah, let's try 13. So we have this matrix A is 2, -3, 3. Oh, that's 14, whoops. 13, we have 3, -2, 3, 4, 1, 4. This vector B is 11, -9, 5. U is 5, -1. And B is 5, -2. So we're going to compute AU, AV, and compare them with B. Could U possibly be a least squares solution of AX equals B? And answer this without computing the least squares solution. See if you can, there we go, cool. Do we need a little bit more time? All right, cool. So what do we get for AU and AV?
AU is 11, negative 11, 11.
Yep. And AV?
7, negative 12, 7.
Cool. Everyone else get this? So what are we going to do with these vectors now that we found? So what's this least squares solution to AX equals B actually doing?
It finds the AX that's like closest to B.
Right. And what do we mean by closest?
There's nothing, the distance, or like B minus AX hat is like smaller, or the length of B minus AX hat is smaller than B minus A, like any other X.
Right. So we're minimizing the distance. And the distance is going to be given by that difference, taking B minus, well, I guess AX for any X. I want the magnitude of this guy, right? So if one of these were the least square solution, it would minimize this distance, right? So the next step is to actually compute these distances for the specific U and the specific V. So we're going to have B minus AU and B minus AV. And what did you guys get for those? We'll be all the way up here. Yeah.
0 to negative 6 for the first.
0 to negative 6. And the second?
I got 4, 3, negative 2.
Yeah, those are right. So if this was a least square solution, this distance would be minimized, so the magnitude of this. So now I want the magnitude of each of these vectors. So what do these magnitudes tell us now?
Like since the magnitude for the AU one is larger, U can't be a solution since you want the distance to be smaller.
Yeah, exactly. You cannot be least squares solution. Any questions about this problem?
So if like they were flipped, would you just say maybe it's a solution?
Yeah, if it's that's going to
Okay.
be, we couldn't definitely say wasn't. You'd have to actually compute this least square solution and then check to see if V is that distance or smaller, or can't be smaller, that distance, exactly.
If they were the same, would you also say both are maybe, or would you say they're both not?
So if you both these, you mean U and V were the same?
Or like root 40, they were both like root 40 or something.
Yeah, then you'd also say it could be either. Or
Okay.
actually, in that case, we need to check if the columns are literally independent, because then it has a unique solution, right?
Mm-hmm.
So they can't both be a solution according to that theorem we had.
So if the columns were Li and they both had the same distance, then they would both not be.
Yeah, because the solution would have to be unique.
Okay.
And if they're two different UV that give the same distance, it won't be a unique solution.
Okay.
Any other questions about Gram-Schmidt or least squares in general? I didn't have too many problems because a lot of the more conceptual ones were on the homework. I want to give you guys a chance to try those first. And the other ones are just pretty straightforward computations. Cool. With the rest of our time, we can do some review from the last chapter. Let me see if I see any good questions. Yep, there's a couple here. So just scroll down. So true or false. For B in, or let's say A is n by n, for B in Rn, B is equal to say x plus y with x in the row space of A and y in the kernel of A. Then projection y hat can depend on the orthogonal basis we use for W, and this is for y has the projection of y onto W, and C space W has finitely many orthonormal bases. So take a couple minutes to think about those three. All right, so first one, is that going to be true or false?
Is it false?
Oh, what makes you say that?
I don't know. I could be wrong, but aren't row A and kernel A the same thing? Or I might be. I'm not.
Not quite. So kernel A is the set of well, cur A is a set of vectors that map to 0, right? Or rather, x where these map to 0. And this is, I mean, it's the row vectors of A. It's also the column vectors of A transpose. There's a couple of different ways to think about this. But earlier in lecture, we went through this proof that says that these guys aren't the same thing. What's going to happen is that they're orthogonal complements of each other.
Then it should be true.
Yeah. And why is that true?
The orthogonal decomposition theorem.
Yep. So if we have these two subspaces which are orthogonal complements of each other, then any vector can be written uniquely as a combination of one vector from each. Then what about the second one? Does this projection of some vector onto a subspace depend on a choice of basis?
I thought the answer might be no, so that it would be false. And I said that this would be because the shortest distance to go from a point and project that onto a different plane or onto a different space would be the same no matter the basis within that plane.
Yeah, exactly. Regardless of basis. So if you have like, say, some plane and some like vector you're projecting onto that plane, it doesn't matter which basis you choose for this plane, right? It's always going to be the same vector, whether you write this vector as a linear combination of like this vector and this vector, or maybe a linear combination of this vector and this vector. I drew in different spots just for like clarity. But yeah, this minimized distance doesn't depend on the basis. And another way you can like see this is, again, using the orthogonal decomposition theorem. There's exactly going to be like one vector here, and this one vector will be the same regardless of like which basis you choose to write it with. Right? Then last one, the space W has finally many orthonormal bases. Is that true or false?
I think it's false because you can like, if you think about like R3 or something and you have like the standard basis, can't you like rotate it like an infinite number of ways and
Yeah.
still get the normal basis?
Exactly. So if you have like, I'll just draw it in R2 to start with. But if you have these two orthogonal vectors, there's definitely many ways you can rotate them, right? You can just take the rotation matrix for like, some data, and there's definitely many data you can pick between 0 and 2 pi. So each of these gives you another orthogonal basis. And similarly, since these guys are all orthonormal, there's kind of similar analogs for Rn, which we can take.
Can you go back up to the question for C or just repeat it?
Yeah, so space W has finally many orthogonal bases.
Perfect, thank you.
Any other questions? Cool. And I sent out the link to the last discussion on B courses.
Is that in files?
Oh, I sent a message to people in my section, but let me post in this chat too, real quick.
Yes, please.
Okay.
Oh, can I clarify on B?
Yeah.
So the idea
Thank you.
is that you have, so like the projection is like you have some vector that's the projection onto the subspace W.
Yeah.
And no matter what basis you write that projection in, it will still like look the same. It might just be like different like numbers because you wrote a different basis, but like that the line or something is like still the same line.
So like the basis we choose for W, it's like we picked a basis to start with for like our space, right? We already have some basis for like Rn, usually the standard basis. So this W is a span of some vectors, and these are all also written with respect to that basis, right?
Mhm.
But since this is like the same vector in Rn each time, whichever vectors you pick for this like V1 through Vn, it's always going to be the same like inherent vector. So it's always going to be the same linear combination of these original basis vectors for Rn, even if we use different basis vectors for W. So it's always going to like be the same actual numbers with respect to this fixed, usually standard basis.
So the projection is written as a linear combination of the basis vectors for Rn.
Yeah, and pretty much in this like last chapter, we've stuck with the standard basis. We haven't done anything tricky with those.
Okay, but
yeah.
So because it's written with the standard basis or like the basis vectors of Rn, then it doesn't matter what you pick for W because it's written with Rn, which is not the basis vectors for W.
Like
right?
We're decomposing this vector uniquely into this, right? So if it depended on our choice of basis, we would have like different y hats, which doesn't work because then this would no longer be unique, right?
Mm-hmm.
So it doesn't matter which basis vectors you pick, this will always be unique. So different basis vectors have to give you the same y hat.
Okay.
Wait, so in like the drawing that you drew for a B, like the basis vectors would represent like the square or like?
Yeah, like these vectors here or these vectors here.
Okay.
Yeah. I could have drawn them in the same place, but it would look kind of crowded. So I just drew two other orthogonal vectors off to the side.
Wait, the basis vectors for the square are for the span or like double, like the basis vectors for W, right? But it's not drawn what the basis vectors for Rn are, right?
Say that again?
So like the one in the picture, like is the basis vectors for W, but is not the basis vectors for Rn.
No, definitely not. They can be completely independent of whichever vectors you have in Rn.
Okay.
Right, like this plane could be lying in Rn in like many different ways. and like each different way will kind of give you a different set of vectors.
Wait, so W is the orthogonal part? Or wait, yeah, what does W represent in the picture?
So W is this whole plane.
Okay, got it.
Yeah. And these little, like these two vectors or these two vectors are different choices for V1, V2.
Okay, thank you.
Yeah. Mhm.
Just making sure, for your lecture on Friday or discussion, will you be posting that to the same space that you posted the Monday lecture
Yeah,
on
yeah.
the drive? Okay,
Yep.
thank you.
All right, on YouTube, not on
YouTube,
Drive.
sorry, YouTube.
Yeah. All right, cool. Have a good day, guys.
Thanks, have a great day.